Okay, so we want to do statistics on all sorts of things. Typically, we want to do statistics on vectors, so multivariate statistics. But you can do statistics on any things, really, numbers, vectors, functions. I even heard about trees. Not very advanced topic just yet. But so what do I mean by that? Well, we want to do description of the data. We want to do modeling. We want to do inference. We want to do machine learning, all these things. And it doesn't matter if you're a Bayesianist or a frequentist or a pragmatist. I mean, in the end, you have to do essentially supervised or unsupervised techniques, and discrete or continuous. So you do classification, or clustering, regression, or dimensional reduction. These are the kind of things that we are very much interested in. So I'll talk about some inference issues today, and Andy will be talking more about some of these very interesting problems. All right. So we have large data sets. We have big data. So what's large? What does it mean something is large? It seems like a pretty obvious question to ask. Okay, you can think of the volume. Well, certainly there is lots of it. And people argue that 100 terabyte today or more is probably a big data set. But really what I think defines a big problem is that when your tools stop working, you can't use your usual strategy anymore. Okay. Sometimes it's not the volume, sometimes the complexity that's complicated. So who knows how much text there is on the internet? Okay. So if you take the whole internet, okay, and forget about images and movies, how much data are we talking about? Any guesses?
10 petabytes.
10 petabytes? Who said less? You said less? It's more like...
More than.
Sorry, more than? Okay, so it turns out it's about 600 gig. Okay, it fits on a single hard drive. Okay, but text mining is still a big problem, and that's because just the complexity is hard and the kind of statistics they do on it is hard. Okay, that's compressed, but still. So it fits on your laptop, right, if you want to. That's why we have the Internet Archive. You just have, yes? Oh, well, it doesn't actually grow that fast, right, because humans write the text. So, I mean, the population grows, so yeah, you do have an increase, but it's actually not that fast, I think. So still, so that ballpark is quite astonishing, I thought. Okay. What, HTML? That's not text. That's not text. Yeah, that's not. Yeah, that's data. Okay, so all right. So data is large. Okay, I put this slide together. Then I realized I missed the point. Okay, it really is large. Okay, so you have to worry about this. So the sample size is large. Okay, and that has really strong implications on our science. So here is just 100 points sampled from a Gaussian distribution. Okay. If I sample 10,000 points, it looks like this. Okay. So what happens is that you start seeing the tails of the distribution, okay, which are really far out. And of course, your data is usually not a nice Gaussian, right? You actually have things that are far, far away, and you have problems, and you have outliers, and so on and so on. So we have to build tools that deal with this automatically. There's no way you can go in and censor our data anymore. Okay. Essentially, starting with Sloan, you don't know your objects anymore. So when I worked on Hubble images very early on, then I remember the Hubble Deep Field, which was a reference catalog for many studies, has 1,540 some objects. And those who worked with it closely knew every one of them by heart. So when I had a problem with some estimations and came to Mark Dickinson, he would say, oh, 847, oh, yeah, forget about that. I don't think I believe the redshift. Okay, so that, just like that. Okay, so we don't have that anymore. We have to be smart about the statistics. just don't know our data. And of course, dimensions are high. Yet another reason why we can't sense our data, because it's really hard to know what's an outlier in high dimensions. Okay? And so the curse of dimensionality, one way to put it is that everybody is lonely in high dimensions. Okay? So everything is an outlier. Everything is essentially on the edge. All right. So here's just a nice picture. You don't have to see it. You have seen images before. To remind you that we are talking about astronomy, and astronomy is beautiful. The galaxies are pretty. You have spirals, you have ellipticals, you have all sorts of shapes and colors. And in fact, Sloan extracts 400 attributes for every one of them. So in our catalogs, we have 400 or 500 attributes that are associated with these measurements. I think sometimes we have probably more parameters extracted than pixels for some of these galaxies. Anyway, so the question is, given Moore's law and the exponential growth, are we keeping up with things? Okay. Well, everything that's linear, we are probably safe with, right? Because the sensors grow at the same rate as our computers. So image processing, catalog extractions, these kind of things, we can probably safely do in the future. But everything else, okay, that's slower will be a problem. And in fact, it gets worse and worse over time. So I think we really have to think about our algorithms and our strategies to, if we want to get the science out of these big data sets. So the question is, so what's more important, to get the correct answer or get the answer fast? Correct answer? Yeah, I figured they would say that. So that's a tricky question, right? Because if you don't get your computation fast enough, you will never get an answer. So sometimes people just take shortcuts and say, we assume this and this and this. And with these assumptions, we can derive some results at least. Okay, and then you can have a look. But that said, I believe that you indeed should be going for the correct answer, and that's the first thing to do, to figure out how to do something correctly, and then look into how you can speed those things up. Okay, so that's kind of the outline for today. I will talk about cross-identification in the first place, and that's the problem when you try to combine different data sets, and these are important to build multicolor and multi-epoch references that you can compare to your models and so on and so on. And then we'll see how far we get with the Bayesian inference, where you can actually infer physical properties from these multicolor measurements. Okay, so cross-identification. This is something that we've been doing since the beginning of time. Okay. So people record their observations, and originally they were drawing it on a piece of paper. Okay, now if you go to the Sky Server, the Sky Server webpage, there are student and kid activities that involve doing exactly that. And so you can take very nice, you can see some of the very nice illustrations that the children do and students do. And then you take the observation and then you go back and revisit the sky because you have a better telescope or you have a different filter or you just want to see what's there through a different pair of glasses. Okay, and that's cross-matching essentially. Of course, now we don't do this, with a pencil and a piece of paper. We do this with surveys. We have these humongous telescopes, and there's these even bigger cameras. You heard about LSST having a 3.2 gigapixel camera. So we have digital data, and that's again what we have to work with. Here is just one motivation to combine these measurements that we make. If you have a multicolor set of observations, you actually see very different physics and very different parts of the galaxies through the different wavelengths. So there's a lot to be learned from these. And also you have the time domain. Also things happen, just go boom in the universe. And You would like to see if you can find those. You would like to link them. You can want to build these curves and understand what happens with them. Okay, there's lots of physics in there as well. So how do we do cross-identification? Okay. It's a hard problem. It's hard computationally because there's lots of data. It's hard scientifically because we don't know what most of the objects are. And it's also hard statistically. We need something that we can use for any observations that we have. Okay? And we want something that works symmetrically on all the observations we want to bring together. Okay? It's a symmetric n-way solution that we are looking for. And also we want something that we can rely on, some quantity that we can use as a selection or a thresholding criterion, and something that we understand. Okay? So I think that often we run into problems with cross-identification because we don't ask the right question. We ask things like how far detections on the sky are from each other, or what is the likelihood of the best position on the sky for that object, or other questions like that. Whereas what we really should be asking is the question, are these detections the same or not? Okay. Do all these detections come from the same object or not? Okay. So we are lucky because you can actually ask that question directly if you do Bayesian statistics. So I would like to tell you this through a very simple analogy. So imagine it's daylight and you can do astronomy. So you just grab a bunch of dice. Okay, so imagine you only have 6 pixels on the sky and the 6 sides of your dice. And the analogy is the following. So you have an object, that's one die. Okay. If you make an observation, that's when you roll it. Okay, you roll the 6, you roll the 3. That's one observation, like a photon coming from a galaxy. Okay. And then there's locality. Okay. So if the die is a fair die, no cheating involved, then you have no spatial constraint. You don't know where the photon is coming from. If it is crooked, if it is loaded and has a piece of lead, on one side, then it will favor one of the sides. And at that moment, you actually learn something about the object. Okay, this is your astromatic uncertainty. When you roll the die and you get a 3, and you know that the die is loaded in a certain way, then you actually learn from that 3 something. Okay? And then the sky is just a bag of dice. Okay? So now what's the cross-match problem? So you draw 2 dice with replacement. What does that mean? So you reach in your bag, you roll the die, and then you put it back, and then you draw it again. Okay, so that's the cross-matching. The question is, did you pick the same die or not? Okay. So the statistical quantity that helps us decide is called the Bayes factor. The Bayes factor is the ratio of the likelihoods of 2 hypotheses. The one that says, yes, they are the same, and the other one says, no, they are not the same. Now, how do you calculate the likelihood of a hypothesis? I mean, you're used to using likelihood functions where you have a model parameter involved. And in fact, that's what you have to do. You have to marginalize over that model parameter. I'll show you how it happens exactly. So you sum over all the possibilities in your model, and that will give you the likelihood of your hypothesis, of your model, if you like. So imagine that you know your astromatic uncertainty, right? You know how the dice are loaded, right? So, for example, if a die is loaded toward the side of 1, okay, then so this says P1 means that this die is loaded toward 1. Then the probability of the data, given that it's loaded toward the side of 1, is a higher number than the others. Okay, so instead of having 1/6 for every one of those probabilities, now you have a higher number for that preferred direction, and you have a lower number for the opposite direction. Okay, and around this die, you have essentially just the same 1/6. Okay, so this is your known astrometric uncertainty, how accurately you can measure something, how much information there is in one observation, okay, in one roll of the die. Okay. So the same thing you can do for the L2 case, 3, 4, 5, 6. Okay, so it's a matrix essentially of probabilities. Okay, so now let's calculate the likelihood that the two die that you picked with replacement are the same. Okay, if they are the same, then they have to have the same loadedness. Okay, they have to have the same L number. Okay, because they are the same. So the lead is inserted exactly the same way into the die. Okay. So that means L1 equals L2. You sum up all the probabilities, and you get this, right? So 1/6 is the prior on L. L can be 6 different directions. We don't know which side it is. We don't know this object. We just know that it's loaded in one direction. We don't know which direction. And this is the product of, this is the likelihood of the L, right, which is the probability of the data. So you thought this is an illustration. No, this is your data. Okay. So you roll the 1 and you roll the 4. Okay. And the question is now, is this the same or not? So the probability of your data is just the product of these two independent things, right? Given the same loadedness, summed up over all the possible loadedness, because we don't know, whether this is an object that's that way or that way or that way or that way. Okay, so that's all. Now, how do you calculate the complementer hypothesis that says they are not the same? Okay, if they are not the same, then L1, the loadedness of the first one and the second one, could be different. Right? Can be the same. You can have a quasar that's right behind the galaxy. Right? So you can have the same position on the sky. You can have the same side for two dies. But they could be different. And that's enough to make this formula different. So what you get in this case is essentially the prior. So the average of the probability of one of the data measurements, right, which is the first row, it was the 1, okay, multiplied by the second one. Okay, you can think of this as here the prior is 1/6, and the other one is the Kronecker delta, and that just essentially makes the two sums into one sum as it collapses the thing. So that's what it takes. Okay, so you take the ratio of these, and you have a number that just drops out, and now you know exactly what people call it sometimes the strength of the evidence for a match. Okay, and you can do the same way for an n-way match. Okay, you can see you can just keep on multiplying here the probabilities, and also you can keep on multiplying these things. So what happens if I had a fair die? If all the dice are fair? Then PL is 1/6 in all cases, okay? So then you have 1/6, okay, times 1/6, summed up to 6. So that's, again, 1/6 times 1/6, so it's, again, 1/6 squared, okay? Now, in this case, you have 1/6 summed up, so that's 1/6 times 1/6, 1/6 squared. So if you have fair case, meaning that there is no information coming from your measurements, then the base factor, the ratio of these two likelihoods is going to be 1. Okay, it means you haven't learned anything. Okay, but if you have locality, if you have really tight constraints on your measurements, then you learn a lot potentially. Okay, so of course we don't have playing dice, and we do things on the sky. But we do the same thing. So you just keep on increasing the size of your dice, and eventually you close your eyes and go from discrete to continuous. and you have to work with density functions in the sky. But it all can be done. The math is the same. And formally, it looks like this. So you have essentially something to start with, which is the precision. Okay, this is a density function that says, given a true position m on the sky, it's a 3D unit vector, just the direction of the object. What are the possible measurements that I could take? That's your uncertainty. That's something you know. It comes from the calibration. Okay, so if I knew where the object was, I can still measure it anywhere on the sky, really, but with different densities. And this is the function that describes that. So people assume, say it's a Gaussian, and say, the x is 0.1 arc seconds, sigma is 0.1 arc seconds, or something like that. Okay, so there's one more thing that's needed to do this, and this is again the same thing as our previous matrix of p-values. Okay. One more thing that's needed is just the prior, 1/6 in the die case. In this case, we have 1/4 pi, anywhere on the sky, really. Okay, the objects can be anywhere. Okay, all right. So then again, you do the base factor thing, which is the ratio of the two likelihoods. The likelihood of the hypothesis age that says all observations come from the same object. Okay, observations are x1, x2, xn. These are the directions of all the sources that I'm currently considering and trying to ask whether these are the same or not. And because they are the same, they have a common position, right? So all x1, x2, xn have to come from that one true location. Okay, I'm just looking at point sources right now. Okay, and the alternative is, okay, so let's look at this. So this is just an integral instead of a sum of something. Oh, before I get there, okay. So you see those things up there. This is the probability density of the data given a hypothesis. Okay. So just to make sure that you know where these come from. So you have heard of Bayes rules, right? And this is very important. So this is just a way to write that, a simple way where you have a model M. Okay, and you have some data D, and you're asking, what's the probability of some parameters in my model? Okay, so when you do some sort of inferencing or fitting, then this is what you typically want to maximize. You want to find out what's the best possible model parameter for your data. Okay, so this is called the posterior probability. Okay, so the red thing is called the prior. Okay, what are the possible model parameters in my model, and how likely are they, or how probable are they? What's the density of those? That's called the prior. Now, this is the likelihood function that people often maximize. Essentially, same thing as maximizing the posterior, assuming there's a flat prior. Okay, so this is the likelihood function. It says, given some model parameter, what's the probability of my data? Okay, and then what you have done here is normalization. Okay, some people call it evidence. So that's normalization, which is really just an integral over theta, integral of this over theta to make sure that this function is normalized. And if you integrate this with respect to theta, then you get 1. Okay, density function. So this is the thing that we actually put in the base factor. Okay, this thing. This is the likelihood of the model. Okay, or the probability of the data given the model, if you like. Okay, so this is that thing there for the two different hypotheses. Just to put things in context. All right, so where are we? So the way you calculate this is, again, just do an integral. And in this case, our theta, our model parameter, is just the one position on the sky, which is m, for which we have a prior, 1/4 pi, anywhere on the sky. And then you have the likelihood function, which is just a product, essentially, of all the different astrometric uncertainties that we discussed on the previous slide. Okay, so for a given true position on the sky, what are the different positions that you could possibly measure? And this is something, again, you can just integrate. Every function here is known. You can just do this. Okay, the alternative is to have different positions for every one of those. And in this case, the whole integral falls apart in a different way because you actually because you have the i's matching each other. So you have the m and the xi all decoupling from each other, and then just have a product of these integrals. So it's even simpler to write and to calculate. So this is what you have to do to get the base vector. And when you do that, you get analytic results, at least for normal distributions and spherical normal distributions called the Fisher distribution. This is a simple 2D case in the limit of high accuracy. And here are sigmas of the Gaussians that are the uncertainties of the measurements. And this is just how it looks. So this is the weight of the evidence, which is the log of the base vector. So when it's 0, we didn't learn anything. But when it's high, then it larger than was positive, then the data supports our hypothesis that they are a true match. Okay, and when it's negative, then the data actually says no, these are not the same objects. Now the problem with, okay, so then also you can do it in the n-way case. Okay, so in general, this is how it looks. So you have the spherical normal distribution called the Fisher distribution, and then you do the math and you get analytic results for this. W is essentially 1 over sigma squared, which is the sigma is your width. Okay, and it's just a nice Gaussian type of thing when you have high accuracies. Okay, now, but the real question is, how do you interpret this base vector? And what does it mean? I mean, I know I can compute it. I know it's an objective number. It's 10 to the 9. What does it mean? What do I do with it? Okay. So you can go to Wikipedia. People do this all the time, right? You go to Wikipedia, and Wikipedia will tell you that if the base vector is 1 to 3, then it's barely worth mentioning. If it tells you it's 3 to 10, then it's substantial evidence. If it's 10 to 30, it's strong evidence. And when you get to 100, then it's decisive. Okay. So this isn't right. This assumes something. Okay. There's something put into this, and that something is a prior. Okay. You always have priors. Okay. And what they assume is that there's a 50% chance for being true or not. Okay, so and that's clearly not the case, and we'll talk about this why. So before I get there, let me just show you something that so we talk about next about the probability of a match. Okay, so that's something we understand. We know what probability is. If it's 0.99, we know it's large. If it's 0.1, we know it's small. Okay, a base vector being 100, maybe you don't know what it means. 10 to the 9. Which one means what. So people say that Bayesian statistics is the math of common sense. Okay, so this is why they say it. Okay, so you have seen the Bayes rule. You all remember the Bayes rule, how it works, right? So now we have Bayes rule essentially written up for both the hypothesis and the complement, and divided by each other. Okay, so what happens is the normalization falls out. Okay, so you see where that comes from. Okay, now you can recognize that this part of the equation is the base vector, so I can just insert that in. Okay, because these two hypotheses are complementars. Okay, I know that pH or the pH complementer is just 1 over 1 minus pH, and similarly the posterior has the same relation. So I can, from this equation, just simply express what the posterior probability is. Okay, and what it means is that if you have a prior knowledge, if you have some idea what things look like, and then you are provided with evidence in form of the base vector, then you can directly compute what your posterior probability should be. Okay, so this is a natural way to express how you update your belief, how you update your knowledge, okay, about something. Okay, so I think this sums it up. So this is how we all function. Our brain works. You learn something. You have an idea how things look like, but then you are presented with evidence. This is how research works, and then you update that and have now hopefully a better understanding. Okay, if the base vector is 1, the posterior is the same as the prior. You haven't learned anything. Okay, so that's the key equation. So now we have the base vector for cross-matching, and we have the equation to figure out what the probability should be. But for that, we need the prior. So what's the prior for a match? So before we get there, we should now look at the whole bag of dice, as opposed to just looking at the measurements that we picked from that ensemble. Okay. So if you have a bag with n dice in it, okay, and you draw one, you don't roll it, don't look at it, put it back, and shuffle, and then draw again. Okay, what's the probability of picking the same thing? Okay, so the first one you can pick anything really. You put it back, and then the probability of getting the same thing for the second time is 1 over n. Okay, so that's it. That's pretty much all the magic to it. So if you do this n times or k times, and just keep on drawing with replacement, you can still figure out what it is. It's going to be n to the power of 1 minus n, or k, just to have different letters. Okay, so that's your prior. In general, what happens is that you have, okay, everybody's okay with this so far? All right, cool. So in general, what happens in astronomy, of course, is we don't have the same surveys. They have different characteristics, they have different thresholds, different wavelengths, and so on and so on. So the selection function for these surveys will be different. Okay, so in one case, you might get bluer objects. In the other case, get redder objects, or you get more distant versus nearby. Okay, so it's not obvious what the prior should be in this case, because we don't have just a single n. We have an n for each and every one of the catalogs that we are currently matching. Okay, so in general, what you have is essentially these numbers and the number of the true matches in your catalog, in the cross-match catalog. So it's kind of a strange situation. You need to know how many matches there are in order to figure out what the matches should be. Okay, but the beautiful thing about this is, in the end, that all these complicated things about the selection functions and their overlaps fall into a single number. Okay, so there's just a single number, n star, the number of objects in your final cross-match catalog that you don't have yet. And this is just an illustration here to show you how different catalogs, I don't think you can see it very well, actually have objects that coincide in space or not. So different selection functions will actually give you very different catalogs. Okay, so that's your prior. And the problem is that it has this unknown fudge factor. You don't know what n star is. The good news is that the formula that we looked at, this Bayesian update formula, the common sense formula, actually is very insensitive to small changes in the prior, as long as there is strong evidence. Another way of saying is that if you have high posterior probabilities coming out of something, that high probability will be very insensitive to small changes in the prior. Okay, so it doesn't really matter what you pick, as long as you're in the right ballpark, you'll be okay. However, you can also solve for this. You can just assume, you can just say that essentially having a constant, you can do this over the sky if it's changing as well, but assuming just a constant prior, then writing this sum over the prior equals n star is an equation that is equivalent to the previous one on the previous slide, because we are summing over all the possible tuples, all the possible combinations. So that will be n1 times n2 times n3 times and so on. Okay, so the first equation is the same as what we had on the previous slide. The second equation, however, is an equation really for n star, because it has the base vector and the prior in it, and hence it has the n star in it. Okay, so this you can actually solve for the n star, and numerically you can very easily solve this by iterating, just picking a reasonable n star to start with, and just in a few iterations it actually converges very fast. Okay, so if you're not convinced yet, we have done simulations to show you that this actually works, and simulated the real universe having proper galaxy correlation functions and all the right number densities and everything that we could possibly match with for this case, which was Sloan and Galax. Okay, so what you can do is you create these objects in a mock universe that have the proper correlation functions, and then you create mock catalogs out of that has the proper uncertainties put in, as well as the selection functions in the form of these intervals. So what you do is that you assign for each mock object a property that's just a random number between 0 and 1. And what you can now do is change the interval of your selection function, and by increasing that or decreasing that, you can change the number density on the sky. Okay? And by having two of these that are matched to the survey parameters that you're trying to do, you can play with the overlaps of those. And by that, you can also match what you see in terms of the overlap. Okay, so how much common objects you see in the two surveys. So these are all matched perfectly to Sloan, and then you actually know what n star is, right? So you know ahead of time what n star is. This is what you get. Okay, so you converge really fast to the true n star, plus a little bit, and that little bit is essentially a little bit of confusion because there are multiple matches here and there. So that's very small change, doesn't really affect anything. But if you really think that this is important for some reason, you have big confusion, then you can calibrate it out by just doing this kind of studies. Okay. So this is how fast it converges, something very simple to do. And then this simulation also showed us that the different multiple matches that we saw in the catalogs between Galax and Sloan were really not artifacts of catalog extraction and image processing, but really were just statistical. So in this case, what we are looking at is one Galax object matched to two Sloan or more Sloan objects, or one Sloan to two Galax or more Galax objects. This matrix is very similar in the case of the true observations as well as this simulation. Okay. So you can just show that there are no problems with your data. It's just statistical coincidences. Okay, so the beauty of this Bayesian algorithm or this whole strategy is, well, first of all, it's analytic, and you can calculate everything very simply. So there's no extra cost of doing the proper thing, okay, over just some heuristics. But also you can extend it, and you can extend it to a limit where crazy things happen, like the stars move. How do you cross-match stars that moved between observations without knowing what their velocity is, proper motion is? It turns out you can. So in this case, what we do is we have not just the position on the sky as a parameter, but you also have the proper motion as a parameter, okay, in which directions the objects could possibly be moving or the stars could be moving. And you marginalize over not just the position, but also the velocities, also the proper motions. And what you see here is essentially a study that looks at Sloan stars with known proper motions and sees if you can associate them at different epochs. So larger and larger they are, farther and farther they are in time from each other, the more they move, then the harder it is to find them. And it turns out, so the open circles are the ones with the analytic case that we looked at. And having a new model that incorporates the proper motion is the stars or the X's, the stars. So what you can see is that the stars indeed assign finite probabilities and not zero to some of the sources that are really far away or really move fast. Okay, they actually get really far away in that time, and you wouldn't be able to find it with just normal matching. Okay, but that said, these are really not very high probabilities. So if by all means, if you had some threshold, 0.9 or something, I don't know what you would want to pick, you would not recover these. But remember, this is just a two-way match. Okay. If you look at the same thing, I think it's more interesting. If you look at these figures, then we're looking at the same time baseline, but between these two observations, which are some years apart, you insert one in the middle, so you actually have one more measurement somewhere. Then you see immediately these probabilities jump up very high, and at that point you can recover them. And it's easy to understand why this happens, and that's essentially a proper motion is practically a straight line, or a great circle, if you like, on the sky. And it's always possible to draw a straight line through 2 points, but not through 3 points. Okay, and that's why you get actually quite a bit of boost there. So this is a very flexible framework to associate sources, and it can be done for events as well, so where you have time domain information and you would like to associate events in space and time at the same time. Okay, so we talked about sky coverage quite a bit, and I will not talk about this, but it actually comes into play to cross-matching as well, and it's very important because when you don't see a match for an object, the question is, why don't I see it? Is it because it's beyond my detection threshold, or because I didn't look? Okay, so maybe it's just not in my field of view. And this is where the sky coverage comes in, essentially telling you whether you should be seeing there something or not. Okay, and as soon as you can do that, you learned a lot from the object already, just by having a non-detection, because you know how far you looked, and you know that it has to be beyond that. Okay, so it actually is a very powerful tool to have, and you can constrain the apparent flux of these objects very easily if you have this information. Okay, and we talked about all these things. Okay, so this was all statistics, but how do we do this in practice? And is it possible to really have tools that do the right thing for this combinatorially hard problem? Okay, so we built a tool called the Sky Query so a decade ago or so that became very popular and was rebuilt into a VO standard, which is called Open Sky Query. I don't know if you have heard of it. It now federates over a dozen surveys across the whole electromagnetic wavelength range, and it's extremely successful. We only know it because every time it goes down, we get angry emails. So people start emailing us right away, within minutes. So they usually notice faster than we do that something went wrong. That's a good sign. But it has some limitations. This is a famous Jim Gray quote that you only have to fear success and failure. So it's a very successful survey, hence demand is high. And the higher the demand, the better your tool has to be, because you have to keep up with all the requests. And because there is all these VO standards and some of the conversions are non-trivial and expensive to do, we had to introduce some limitations on the number of rows you can return and things like that. So in addition to that, it also doesn't do the proper Bayesian thing because it was written before that was figured out. So we set out to create a new service and a new engine that will do this in a scalable way on a cluster of machines that talk to each other in the most efficient way, and essentially provide the VO interface on top of that. So we are building this dynamic federation right now, and in fact, we are going to release it real soon. This summer is the plan, where you can come in and submit a job, a query essentially, against these independent databases that we know of. And those get automatically cross-matched. So you will be running a query that's very much like a SQL query, but it does the cross-matching for you on the fly. So you don't have a join between tables, you have a cross-match between tables. Okay. So, and this will have the proper probabilistic Bayesian algorithms all put in. All right, so here's how a query looks in SQL. You select your columns from one catalog. In this case, the SD-SSDR7 photo of Joe, that we call P. And cross-join that with the SD-SSDR7 spectroscopic objects. It's just an example. And let's call that S. Okay, so cross-join is actually a real SQL keyword. And what it does is it creates all the combinations that you could have. This is the Descartes, the outer product. Okay, so that's something you don't want to run this query, but it's very SQL. And you have the where clause, and the into just says where you want to dump the results. Okay, select into. So the results should be going into a table called xtest in this case. Okay, so what we do with this query is we extend it by adding a special cross-match clause that enables us to make sure that the requests that come in are parsable and can be verified before execution that they make sense, and B, they have the ability to describe all the details we need for doing a proper cross-match. This is how it looks. Okay, so the cross-match clause has a qualifier that says what type of cross-match would you like to perform. In this case, we do the base factor. Okay, it's called the Bayesian. Whatever you do during a cross-match will produce extra information. Okay, so say you want to create, say it's just the best position based on the measurements. Okay, so you have positions coming here, 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 and the average of that, or the weighted average of that, is right here. Okay, so you would like to know, based on all these measurements, what's the best position there is for this object, or what's the best constraint there is for this object. So that, for example, one of the things that comes back from this query. So the X, this cross-match, behaves like a table in a way. That's yet another reason why it can be just a simple SQL constraint, just a where clause. And then we specify what we are matching. Okay, so we are matching two tables, P and S, and we are matching on positions that are defined by the RA index of those tables. So you could imagine a different table would have alpha J2000 as the column name instead of RA. So you can specify explicitly what you want to join on. And then comes three strange numbers. Okay, they are the same in this case. Now, those things are to enable you to put in variable astrometric uncertainty. Okay, so essentially you can include a SQL expression there that can be evaluated into a floating point number, which is your sigma, essentially. Okay, and because that varies for the whole catalog, you have to also specify a min and a max value, so we know ahead of time, what the math should be, what are the kind of candidates we have to keep to do the whole cross-match properly. So this works not just with two catalogs, but also works with n catalogs. So you can just keep on enumerating a bunch of tables here, and it will work like that. Okay. Having limit is where we draw the line. We want a base factor to be larger than 10 to the 3. Okay. So it's a very simple construct, but it's extremely powerful, and it's flexible. It will enable us to create services that will do different kinds of cross-matching for people who want to use a distance threshold, or you want to use a probability threshold instead of just the base factor, and so on and so on. So this is our goal. Okay, so this is too good to be true, isn't it? I mean, if you had this tool, imagine all the things you could do. Well, it exists. Okay, so we actually have this website already running, and I was playing with it just this morning. I wonder if I can find it quickly. Maybe I shouldn't spend too much time looking for it, but there's this Open Sky Query. This is the new Sky Query engine. And you have the schema browser, query, job history. You can, this is the query that I just ran. And when you go to your MyDB, this X-test table shows up. Okay. Good. What would you like to see? Oh, you're not seeing the. I was happy that you don't see the URL, because if you go there and start hitting the service, then okay, here we go. All right. So that's the Sky Query web page, and that's no, I don't see it. So then you have just the schema browser where you can figure out which table has what columns. And you have your queries, the job history, and the MyDB. And if you go to your MyDB, that already lists this X-test table, which we just created with this query, and it tells you what the columns are that were put in. Okay, and you can also hit peek, and it will dump a bit of the data, essentially just so you can peek in, and you can export it into files, and you can get these things. So it has a job queue, and you can submit requests. If you're going to go there now and hit it, Manu, I see you are looking at the URL. Then, okay, I'll have a word with you afterwards. Okay, so let's go back. Okay, so oops. All right. So Rick already promised you that I'll talk about the Hubble Legacy Archive cross-match catalog, and this is a very interesting project that we recently almost released. It's a beta version that's already out there. It's a very interesting project that essentially tries to make use of all the Hubble observations that there have been ever taken and cross-match those so that you can do multicolor and multi-epoch studies on that. Now, it turns out that because Hubble has a tiny field of view, there aren't many calibrator stars that you could use to pin down the astrometric accuracy. Okay, so even though the telescope has extremely good astrometry within a field, or relatively speaking, but across the fields, there's enough uncertainty in the position of the fields that it's hard to do cross-matching. Okay, so you have to do some sort of solution and some refinement of the astrometry. And when people talk about astrometric corrections, you usually think of trigonometric equations, lots of sine and cosines, and very expensive minimization. So the idea we came up with here is to solve a simpler problem and assume that you can just take a 3D rotation to match these uncertain positions to each other, and essentially use the objects within the fields themselves instead of some external calibrator set to pin down where things are. Okay, so even that is hard. A 3D rotation in general is pretty complicated. So instead of doing that, we use infinitesimal rotations, which is essentially just a very simple formula that looks like this. Where is it? Here. Looks like this. And this essentially makes our minimization problem into a linear equation. So you can just come up with a linear equation for the best solution and just quickly solve these things in linear time. Okay. So this was what enabled us to essentially go from something that's very uncertain, and as the separations are quite far away and random, to something that is really peaked at very high accuracies, and this is typically sub-pixel accuracies. So we are essentially at the limit where we can get for most of the cases. Okay, So again, we are looking at, I don't even know, a few milli-arc-second accuracies. And again, compared to the red is extremely good. So what we do then is we find friends of friends groups, much like you would do it with halo finders. And then you have to essentially break up these friends of friends groups into, because they potentially have these dumbbell structure and these chains that you can form. And we use Bayesian model selection that is very much like the cross-matching we talked about. In fact, the math turns out to be the same. Essentially, you compare base factors for different kinds of combinations of groupings. And essentially, you can look at what the fluxes are, and it turns out that it does the right thing. So I'm running out of time, so I won't talk too much about it. And this just shows you how many objects there are. So this is something that is an effort that was worth doing. We have millions of sources that are matched, and we come up with millions of matches. And as you look at the time span, even at 1,000 days, so many years, you have lots of sources to play with. So this is a very, very valuable data set. And this is just another figure that shows you how many detections there are. And because we have sky coverage information, we can also go after the dropouts. So, all right. So maybe quickly I say something about the zonal algorithm just to get some practical things as well into it. And this is how the sky query works, for example, is essentially a similar technique that we used for the sky indexing and the 3D indexing we talked about. You divide and conquer, okay? But now what you do is you divide the sky into zones, constant declination stripes, and what this gives you is the simplicity that there are only two neighbors up and down, okay? And then essentially sorting within the zone gives you a really simple way to essentially stream data into a cross-match engine and have a very fast evaluation of formulas that we want to compute. So with this, you can do the largest catalog Sloan is 400 million versus Galaxy in about an hour. Okay, so that's extremely fast compared to previous methods that people try to do and usually fail. They're just simple scripts don't work anymore at that scale. And it turns out we are still limited by CPU. Okay, so you would like to do something fast, and of course, when you do something fast, you go to GPUs. Okay, so now we just released a new, I guess I call it the beta version of our cross-matching code that runs on multiple GPUs. So it uses Thrust and custom CUDA kernels to run the cross-match on. We have tested up to 6 GPUs. That's how many we could fit in a single machine, and it has just great performance. So even on the gaming cards, we can do 30 million versus 30 million in just 11 seconds. If I want to do the whole Sloan versus Galaxy on several GPUs, Tesla cards, it runs in 3 minutes. Okay, so this is the kind of scaling that you hope to get, and what this enables us to essentially scale up soon to the big challenges of LSST and the next surveys. Okay. So that's exactly on time. So maybe I'll just go to the, well, I won't even go, just essentially summarize in words what we have talked about. And that's essentially Bayesian statistics. Okay, so Bayesian inferencing and Bayesian statistics can help you quite a bit and often turn out to be simple. Okay, so you don't have, just because you have lots of data and because you have data tsunami, right? And you have lots of dimensions, you don't have to get shy away from the real math. And once you figure out what you want to do, then you can just speed things up. And by doing the proper Bayesian things, you enable new type of applications, again, matching stars, time domain comes in, and what we haven't talked about is essentially, and didn't have time, is folding in the multicolor information. So once you have matched these catalogs and you have all the magnitudes and fluxes measured, then you can actually use that information as well. So it helps your cross-matching. Sometimes it's just not enough to have positions, as well as it helps you to understand what the properties of these objects are. So thank you. Any questions? Yes?
Your cross-matching depends on the fact that you have two catalogs, which you extract from images independently of each other.
Mm-hmm.
You do better by actually somehow cross-matching the two images, or it would maybe get maybe better, deeper source catalog.
So, right. So there are several issues that come up when you want to work with images. Okay. Yes, there are certain cases when you can actually gain extra information, and yes, stacking of images could get you potentially deeper. The computational challenge is much more significant, because with catalogs, you actually have fast methods to work with these things, whereas with images, well, you just have to crunch through a whole lot more numbers, a whole lot more data. But that said, even then, it's not so simple to work with images sometimes, because they are very different. So you have very different blurs and point spread functions and instruments. So matching up those things is far from trivial, and there are research projects currently going on to deal with those. At all levels, even at the survey level, to just do better combinations of images. But I don't think that's an alternative to cross-matching in many ways. Cross-matching essentially gives you that, but based on the models of the images. I mean, catalogs are, in many ways, just the models of your images. So the parameters that you extract for each object is a description of what's there, and then in principle, you could create images from the catalogs, and this is what the SST imaging pipeline does, image simulation pipeline does, and we talked about that, right? So you can take a catalog of objects and then simulate it and create images from that. So you can go back and forth, back and forth. That's active research. Yeah.
Recommendation on an introduction to Bayesian statistics?
Introduction to Bayesian statistics. You mean books? Which book? Or website. Besides this, I can definitely recommend some books. We can talk in the break. Yeah. Perfect. So Andy will tell you even more. Okay. So maybe after his talk, if he leaves anything for me, then I can recommend some more books. Okay. All right. Yes.
You might have said this yesterday. What do you use the GPUs for? What list of functions are you finding GPUs
right. So in this case, because cross-matching does have to look through a lot of combinations that could be potentially matches, right? We do this big problem on it. So we actually fire up threads that look at all most possible combinations, at least within the zones, of the sources, and measure actual distances between them to figure out what are the candidates we should be considering for the Bayesian analysis. And so essentially the GPUs select all the candidates for us, and then we just run on those candidates. It's a very generous threshold, and we run the Bayesian statistics on that pair list or on that tuple list that comes out of that.
Anything else?
Oh, so yes. I mean, in general, we use the GPUs for other things as well. I mean,
that's what I'm asking.
This project only uses that. So I did talk about the cross-correlation function, or the correlation function measurements that we have used, and it's a big project on its own, and that's the one that was used for the BAO measurements and integrated with the SQL server. We also have a project that is looking at imaging problems. So essentially, it's exactly the goal, essentially, to have fast and better combinations with images. And yeah, there is the Richard, who's mate, he does gene sequencing, DNA, and on the GPU and databases. So with the group, there are quite a lot of work. There is random forest implemented on GPUs, so we can do photos very fast. And Alex mentioned this very low power cluster called the UMDA blades.
Multi-dimensional FFTs.
Oh, absolutely. Yeah. FFTs.
The practical limit is how much data can you fit onto the GPU memory?
Right.
So you may have to break it up into multiple 1D.
Shuffle it back.
Yeah.
That's right. That's right. They're very fast. So the numbers, I mean, it's a factor of 100 essentially. So GPUs do much faster FFTs. Yeah. There's a lot of libraries that I mentioned yesterday to do these kind of things, and NVIDIA supplies optimized versions. So BLAS is there, FFT is there. You have sparse matrix calculations. You have imaging libraries. You have.
So in the Hydro community, quite a few codes have been ported over to GPUs and this code, and then shared in the community.
Yeah.
So that's typical use of our GPU cluster used by a lot of Hydro guys who want to do.
Yeah. So at the GPU Technology Conference, when the NVIDIA CEO or president gave the keynote, he actually showed an embedded simulation that was running on the GPU, and it's just amazing. I mean, it was good before, but it's just amazing the kind of detail they could achieve on a single machine now. So it's the latest Kepler cards just run really fast. Yes.
How do you do load balancing? Because you'd expect that when you're matching, like with the defined
Right.
like a region, some sources will have many other potential matches.
That's right.
So how do you deal with that?
That's right. So it's implementation is using multiple GPU threads to drive multiple GPUs, and essentially what happens is that you have to chop it up. Your catalog is just too big, so you have segments of that cases, and you have to look at all the combinations. So in a way, you have a matrix of jobs, and then the threads or the workers, if you like, come in and get a new job every time they finish. Now that's actually optimized such that they will preferentially get a job that already is loaded onto the GPU. So at least one of the two catalogs is already sitting on GPU memory, so you can save on transferring the data to the GPU. That said, it's not a huge effect. It's probably a 10% increase in performance. So because we have quite a bit of computing to do, it's not, the memory bandwidth that people complain about is not an issue in this case, for example. Yeah, it really is fast. Yeah. Okay, any more? No, in that case, it's coffee time.